Right now, somewhere in the equations that describe the entire universe, something does not balance. Not a small rounding error, not a minor correction, a difference large enough that some physicists have started whispering a possibility that would have sounded absurd just 20 years ago. The model of the universe might be wrong. For the past 100 years, cosmology has been one of the most successful scientific stories ever told. Humans discovered that the universe is expanding. They measured the faint radiation left behind by the Big Bang. They mapped galaxies across billions of light years and built mathematical models that could predict how the cosmos evolved from a hot cloud of particles into the vast structure we see today. The equations worked beautifully, until they didn't. Somewhere between the birth of the universe and the present moment, something in the numbers stopped lining up. Two of the most precise measurements in science disagree about how fast the universe is expanding. The leftover radiation from the Big Bang appears to contain a strange alignment that should not exist in a universe with no preferred direction. The early universe should have produced far more lithium than we can find anywhere today, and the matter in the universe appears to be distributed differently than our best models predicted. Each of these problems might have been dismissed as a minor anomaly, but together they form a pattern, and patterns make scientists uneasy, because patterns sometimes mean something deeper is wrong. In the next few minutes, you are going to discover why two different measurements of the universe's expansion give two completely different answers. You will meet the scientists who first realized something didn't add up. You will see why the oldest light in the universe appears to point in a direction that should not exist. And you will learn why some cosmologists now believe we may be standing at the edge of a scientific revolution. If this sounds like the kind of mystery that keeps you awake at night, consider subscribing, because the universe is stranger than we thought. Take a breath. We are heading into the deep. For most of human history, the universe looked perfectly still. The stars rose and set, constellations held their shapes. The sky appeared permanent. But in 1929, an astronomer named Edwin Hubble made a discovery that permanently shattered that illusion. He was studying distant galaxies through the telescope at Mount Wilson Observatory in California. At the time, astronomers had only recently realized that those faint smudges in the sky were not clouds inside our galaxy. They were galaxies themselves, entire island universes filled with billions of stars. Hubble began measuring how their light was stretched as it traveled through space. This effect is called redshift. When an object moves away from you, the waves of light it emits stretch slightly, shifting toward the red end of the spectrum. The faster it moves away, the more the light stretches. What Hubble found was astonishing. Nearly every galaxy he observed was moving away from us, and the farther away a galaxy was, the faster it was receding. The universe was expanding. It was not simply filled with galaxies drifting through empty space. Space itself was stretching. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart, not because they are moving across the rubber, because the rubber itself is expanding. That is what the universe is doing. Every galaxy, every cluster, every cosmic structure is being carried outward by the expansion of space. This discovery was one of the most profound moments in the history of science, because it meant something extraordinary. If the universe is expanding today, then in the past it must have been smaller, hotter, denser. Run the expansion backward far enough, and everything converges toward a single moment. A beginning, the Big Bang. For decades after Hubble's discovery, astronomers refined this picture. They built better telescopes, measured more galaxies, improved their models, and gradually they realized something remarkable. The expansion of the universe could be measured with extraordinary precision. All you needed to do was determine two things: how far away galaxies are and how fast they are moving away from us. Divide one by the other and you get a number that describes how quickly the universe is expanding at this moment in time. This number is called the Hubble constant. For a long time, measuring it was extremely difficult. Distance in the universe is tricky. You cannot stretch a tape measure between galaxies. Instead, astronomers built what they call a cosmic distance ladder. First, they measure distances to nearby stars using parallax. Then they use certain types of stars whose brightness is well understood. Then they use exploding stars called Type Ia supernovae, which shine with nearly identical brightness and can be seen across vast cosmic distances. Step by step, they built a ladder reaching across the universe, and by the early 2000s, the measurements began converging toward a clear answer. The universe appeared to be expanding at roughly 73 kilometers per second per megaparsec, which means that for every 3.26 million light-years of distance, galaxies move about 73 kilometers per second faster away from us. It was precise, elegant, consistent. For a moment, it looked like the story of cosmic expansion had finally been solved. But the universe had other plans, because another group of scientists was measuring the expansion of the universe in a completely different way, and their answer was not the same, not even close. 2 numbers. That was all it took to unsettle an entire field of science. For most of the 20th century, astronomers believed that if you measured the expansion rate of the universe carefully enough, every method would eventually converge on the same answer. The universe expands at one speed. It cannot do otherwise. Space does not stretch in 2 different ways at the same time. That assumption seemed reasonable, but assumptions have a habit of breaking, and here is where the story begins to twist. While one group of scientists was measuring the expansion of the universe by observing exploding stars in distant galaxies, another group was looking much further back in time, not millions of years, not billions, almost all the way to the beginning. They were studying the cosmic microwave background, the faint radiation left over from the Big Bang itself. To understand why this matters, imagine the universe when it was less than 1 million years old. At that time, space was not filled with stars and galaxies. It was filled with an incredibly hot plasma of particles and light. Electrons, protons, and photons bounced around in a dense fog, so bright and energetic that light could not travel freely. Every photon was constantly scattering off charged particles, ricocheting through the young universe like a beam of light trapped inside a cloud. Then something changed. As the universe expanded, it cooled. Roughly 380,000 years after the Big Bang, temperatures dropped enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly the fog cleared. Light was free to travel, and that light is still traveling today. It fills the entire universe as a faint microwave glow that arrives from every direction in the sky. This radiation is the oldest light we can observe, a snapshot of the universe when it was only a few 100,000 years old. In the early 2000s, satellites like WMAP and later Planck mapped this radiation with extraordinary precision. They measured tiny fluctuations in temperature across the sky, variations so small they amount to only 1 part in 100,000, but those fluctuations carry enormous information. They encode details about the density of matter in the early universe, the amount of dark matter, the amount of ordinary matter, the curvature of space, and crucially, the rate at which the universe must be expanding today if our model of cosmology is correct. Scientists took the data from the Planck satellite and fed it into the standard model of cosmology, a model called Lambda CDM. Lambda represents dark energy. CDM stands for cold, dark matter. Together they describe a universe made mostly of invisible components, expanding under the influence of gravity and dark energy. The model is extraordinarily successful. It explains the formation of galaxies, the large-scale structure of the universe, the temperature patterns in the cosmic microwave background. It is one of the most precise theoretical frameworks ever created. When scientists used this model to calculate the expansion rate of the universe from the early universe data, they obtained a number, 67 kilometers per second per megaparsec. That number is extremely precise, but it is not the same number astronomers measured using supernovae and nearby galaxies. Not even close. One measurement, says 73, the other says 67. The difference is small enough to sound harmless, 6 kilometers per second. But in cosmology, this gap is enormous. It is far larger than the expected margin of error, large enough that statisticians began calculating the probability that both measurements could still be correct. The odds were shockingly low, less than 1 in 1,000, and the more precise the measurements became, the worse the disagreement grew. The problem became known as the Hubble Tension. Two of the most precise experiments in modern astronomy were telling two different stories about the universe. Imagine measuring the speed of a river using two methods. In the first method, you drop leaves into the water and time how long they take to drift downstream. In the second method, you analyze satellite images taken decades apart and calculate how far the river has widened over time. Both techniques are precise. Both techniques are trusted. But one method says the river flows at 10 miles per hour. The other says 14. That difference cannot be explained by rounding errors. Something deeper must be wrong. Either one measurement is flawed, or our model of how rivers work is incomplete. Cosmologists hoped the problem would vanish with better data. Perhaps the supernova measurements contained subtle calibration errors. Perhaps the Planck satellite had missed something in its analysis. But as new telescopes came online, the opposite happened. The measurements improved, and the tension remained. Then a Nobel Prize-winning physicist named Adam Rees pushed the measurements even further. Rees and his team refined the cosmic distance ladder using improved observations from the Hubble Space Telescope. They measured distances to Cepheid stars with unprecedented precision, calibrated supernova distances more carefully than ever before, and recalculated the expansion rate. Their answer was not smaller, it was slightly larger. The tension had grown, and here is the part that made people nervous. The cosmic microwave background measurements were also becoming more precise. Planck's data was extraordinarily clean. Independent analyses confirmed the result again and again. The early universe predicted an expansion rate near 67. The local universe insisted on 73. Both measurements appeared correct. Both were backed by decades of research. Both relied on entirely different physics, and neither would move. For years, cosmologists searched for mundane explanations, instrument errors, calibration problems, statistical anomalies. One by one, these possibilities were investigated and eliminated. The tension refused to disappear, which left a more uncomfortable possibility. The model itself might be wrong, but that possibility raised an even bigger question. If the standard model of cosmology is incomplete, what exactly is missing from our understanding of the universe? And that is where the story gets far stranger, because the expansion of the universe is not just happening, it is accelerating, and nobody knows why. For most of the 20th century, scientists believed the expansion of the universe should be slowing down. The logic seemed unavoidable. Gravity pulls things together. Galaxies attract each other. Clusters of galaxies attract other clusters. If the universe began with a violent expansion, gravity should gradually be working against it, pulling everything back, slowing the cosmic expansion over time. Like throwing a ball into the air, it rises fast at first. Then gravity takes over. Eventually it slows, stops, and begins to fall. For decades, cosmologists believed the universe must behave the same way. The only question was how fast the expansion was slowing. By the late 1990s, two independent teams of astronomers set out to answer that question. One team was called the Supernova Cosmology Project, led by physicist Saul Perlmutter. The other was the Heisey Supernova Search Team, led by Brian Schmidt and Adam Rees. Their strategy was simple in principle: find distant type Ia supernovae. These stellar explosions are incredibly useful because they shine with nearly identical brightness. That means astronomers can determine how far away they are by comparing how bright they appear from Earth. The dimmer the supernova looks, the farther away it must be. By measuring both the distance and the redshift of these supernovae, the teams could reconstruct how the expansion of the universe had changed over time. If gravity were slowing the expansion, distant supernovae should appear slightly closer than expected. Because billions of years ago the universe would have been expanding faster, the teams collected data, dozens of supernovae, then more, then many more, and when the calculations were complete, the answer shocked them. The supernovae were too dim, too far away. The universe had expanded more than expected, which meant the expansion had not been slowing down. It had been speeding up. Gravity was losing. Something else was pushing the universe apart. Something enormous. Something invisible. The teams checked their data again. Then again, both groups arrived at the same conclusion. The expansion of the universe is accelerating. When the results were announced in 1998, the reaction in the scientific community was immediate. Confusion, excitement, and disbelief, because the equations of cosmology did not predict this behavior. Acceleration requires a force that works against gravity, a kind of cosmic pressure that pushes space outward. The simplest way to include this effect in Einstein's equations was something he himself had once proposed and later rejected, a term known as the cosmological constant, a form of energy built into the fabric of space itself. Today, we call it dark energy, and it appears to dominate the universe. Current measurements suggest roughly 70% of the cosmos is made of this mysterious energy. Dark matter accounts for about 25%. Ordinary matter, the atoms that make up stars, planets, and people, represent only 5%, which means that everything humanity has ever seen or touched is a tiny minority of the universe. The rest is invisible and poorly understood. Dark energy behaves like a strange kind of pressure. As space expands, more space is created. And if dark energy is intrinsic to space itself, that means the total amount of dark energy increases as the universe grows. More space, more dark energy, more acceleration. It is a feedback loop that causes expansion to speed up over time. On the largest scales, gravity cannot compete. The universe becomes dominated by acceleration. Galaxies drift farther apart. Clusters become isolated. Eventually, trillions of years from now, the observable universe will contain only the remnants of our local group of galaxies. Everything else will have disappeared beyond the cosmic horizon. That is the long-term future predicted by our current cosmological model. But here is the unsettling part. Dark energy fits the equations. It explains the acceleration, but we have no idea what it actually is. It has never been detected in a laboratory. No particle experiment has observed it. No physical theory predicts its observed value. In fact, when physicists try to calculate the energy of empty space using quantum mechanics, they get an answer that is catastrophically wrong. Wrong by a factor of about 10 to the power of 120. It is the worst prediction in the history of physics. The numbers simply do not match reality, which means the thing responsible for most of the universe's behavior is something we cannot explain. And here is where the tension becomes more troubling. The standard cosmological model assumes dark energy behaves as a constant energy density. It does not change over time. It does not evolve. It simply exists. But if dark energy were even slightly different than we think, the expansion history of the universe would change, which means the predicted value of the Hubble constant from the early universe might also change. Some physicists began wondering whether the Hubble tension might be a hint, a sign that dark energy is not constant after all. Perhaps it changes slowly over time. Perhaps it interacts with dark matter. Perhaps it represents a completely new kind of field we have not yet discovered. But these ideas introduce new complications and new problems, because when scientists modify the cosmological model to fix one tension, they often create another. The universe refuses to cooperate, and then something even stranger appeared in the oldest light we can observe. A pattern that should not exist at all, a direction in the universe. And that discovery forced scientists to confront a deeply uncomfortable possibility. The universe might not be as random as we thought. The cosmic microwave background should be the most boring thing in the universe. not because it is unimportant, because it should be almost perfectly random. The light we see in the microwave background was released when the universe was only about 380,000 years old. At that time, matter had barely begun to organize itself into structure. There were no galaxies yet, no stars, no clusters, just a nearly uniform sea of particles and radiation. The tiny temperature variations we observe in the microwave background are the seeds from which all cosmic structure grew. Regions slightly denser than average eventually collapsed into galaxies. Regions slightly emptier became cosmic voids. But on the largest scales, the fluctuations should be statistically random. The universe should have no preferred direction. It should look roughly the same, no matter where you look. This assumption is called the cosmological principle, and it sits at the foundation of modern cosmology. But in the early 2000s, something unexpected appeared in the data. When scientists analyzed the microwave background maps produced by the WMAP satellite, they noticed that some of the largest temperature patterns seemed to be aligned, not randomly distributed, aligned along a particular axis in the sky. At first glance, the effect seemed subtle. Cosmic microwave background data is messy. Foreground radiation from our own galaxy must be carefully removed. Instrument noise must be accounted for. Statistical patterns can appear by chance in complex data. Many scientists assumed the alignment would vanish as the data improved. Then the Planck satellite launched. Planck mapped the cosmic microwave background with far higher resolution and sensitivity than WMAP. If the alignment were an artifact, Planck should erase it. Instead, the alignment remained. Large-scale temperature fluctuations appeared to share a common orientation, a direction. This was deeply unsettling, because if the universe truly has no preferred direction, such an alignment should not exist. The probability of the observed alignment appearing by random chance is low. Not impossibly low, but low enough to raise eyebrows. Some physicists began referring to the anomaly with a slightly mischievous name, the axis of evil. The name is not meant literally. It is a reference to a phrase used in politics during the early 2000s. But in cosmology, it refers to something much more subtle and strange. A possible axis, embedded in the oldest light in the universe. Imagine rolling dice millions of times. You expect the results to scatter randomly, but suppose every few thousand rolls, the dice begin landing in patterns that align along the same direction. Not enough to prove the dice are rigged, but enough to make you uneasy. That is what the axis of evil represents. A pattern that should not be there, yet appears consistently across multiple measurements. The problem becomes clearer when you consider what the microwave background represents. This radiation comes from the entire sky, every direction. If the universe has no preferred orientation, then the temperature fluctuations should not align along any particular axis relative to us. And yet the observed pattern appears to line up suspiciously close to the plane of the solar system, which raises an uncomfortable possibility. Either the alignment is a coincidence, or something about our local environment is influencing the measurement, or our understanding of the early universe is incomplete. Scientists have spent years trying to explain the anomaly. Some propose subtle foreground contamination from our galaxy. Others suggest statistical coincidence. Still, others explore exotic physics. Perhaps the early universe experienced unusual inflation dynamics. Perhaps space itself possesses a faint global anisotropy. Perhaps unknown physical fields influence the distribution of primordial fluctuations. Each explanation solves one piece of the puzzle, but none has convinced the entire community. The anomaly refuses to disappear, and here is where the unease grows. Because the axis of evil is not the only thing that does not fit the standard cosmological model. Elsewhere in the universe, another discrepancy has been quietly bothering physicists for decades. A problem involving one of the simplest elements in existence. An element created in the first few minutes after the Big Bang, lithium. The universe appears to be missing it. The story of lithium begins just minutes after the universe was born. At that moment, the universe was unimaginably hot. Temperatures were measured in billions of degrees. Protons and neutrons were flying through space like sparks in a furnace. In this chaos, the first atomic nuclei began to form. This process is called Big Bang nucleosynthesis. It lasted only about 20 minutes, but in those 20 minutes, the universe created the first elements that would ever exist. Hydrogen formed first simple nuclei containing a single proton. Helium followed, built from 2 protons and 2 neutrons. Tiny traces of other elements appeared as well: deuterium, helium, 3, and lithium, 7. The proportions of these elements depend on the density and temperature of the early universe. That means, if we know the physics of nuclear reactions, and we do, we can calculate exactly how much of each element the Big Bang should have produced. And for most elements, the predictions match observations beautifully. Hydrogen and helium appear in almost exactly the proportions predicted by theory. Deuterium measurements agree with extraordinary precision. For decades, this was considered one of the greatest triumphs of modern cosmology. The Big Bang model did not just describe the universe, it predicted the chemical composition of the cosmos. But lithium refused to cooperate. According to the calculations, the early universe should have produced about 3 times more lithium, 7 than we observe today in ancient stars. The discrepancy has persisted for decades. Astronomers first noticed it in the 1980s, while studying extremely old stars in the halo of the Milky Way. These stars are ancient, more than 12 billion years old, and they preserve the chemical composition of the early universe. When scientists measured their lithium content, they expected to see the predicted abundance. Instead, they saw far less. Not slightly less, much less, 3 times less than theory predicts. This became known as the cosmological lithium problem. At first, scientists suspected the stars themselves might be destroying lithium. Lithium is fragile. Inside stars, nuclear reactions can easily burn it away. Perhaps the lithium had been present initially, but was later depleted. Astronomers examined this possibility carefully. They studied large samples of old stars across different regions of the galaxy. They analyzed stellar atmospheres. They modeled internal mixing processes. The result was surprising. The lithium levels appeared remarkably consistent across many stars, as if they all started with the same low abundance, not the higher value predicted by Big Bang nucleosynthesis. The discrepancy remained. Some physicists proposed exotic solutions. Perhaps unknown particle interactions occurred during the early universe. Perhaps decaying dark matter altered nuclear reaction rates. Perhaps some aspect of nuclear physics in the first few minutes after the Big Bang behaves differently than expected. Each idea was explored. None provided a fully satisfying explanation. And here is the uncomfortable part. Big Bang nucleosynthesis depends on the same underlying cosmological model used to interpret the cosmic microwave background. The same model involved in the Hubble tension. The same model that assumes dark energy behaves as a cosmological constant. When lithium refuses to match the predictions, it does not necessarily mean the Big Bang theory is wrong, but it does suggest that something in our model is incomplete. Another small crack in the framework, and cracks, when they begin to multiply, attract attention. Because cosmologists began noticing another discrepancy emerging in completely different observations, a tension involving the clumpiness of matter in the universe, a quantity known by a technical name, shuit. Imagine standing on a hill overlooking a vast landscape after a storm. Water has drained through the terrain, collecting in valleys and carving channels through the soil. Some areas are smooth and empty. Others are dense with winding rivers and deep basins. Now imagine trying to describe that landscape using mathematics. You would need to measure how clumped the water is, how strongly the valleys gather matter, how empty the empty spaces really are. Cosmologists face a similar problem when they study the universe. After the Big Bang, matter was distributed almost perfectly evenly, but over billions of years, gravity amplified tiny fluctuations. Regions slightly denser than average began attracting more matter. Those regions collapsed into galaxies. Galaxies gathered into clusters. clusters connected through enormous filaments of dark matter stretching across hundreds of millions of light years. Between them, vast cosmic voids expanded. The universe today resembles a giant web, our cosmic web, and scientists have developed ways to measure how strongly matter has clumped together over time. One of the key parameters describing this is called S8. It is essentially a measure of how lumpy the universe has become. If gravity is working exactly as predicted in the standard cosmological model, matter should cluster to a specific degree, not too much, not too little. The value of S8 predicted by the model can be calculated using the same cosmic microwave background data from the Planck satellite. That calculation gives a clear answer. But when astronomers measure the clumpiness of matter directly using observations of galaxies and a phenomenon called gravitational lensing, they obtain a slightly different result. The universe appears less clumpy than expected, not dramatically less, but consistently less, just enough to create tension. This discrepancy became known as the S8 tension, and like the Hubble tension, it involves two extremely precise measurements that should agree. One derived from the early universe, the other from the present-day structure of galaxies. Both methods are trusted. Both rely on completely different observational techniques. And once again, the numbers refuse to line up. Short sentence, it didn't add up. To understand why this matters, consider another analogy. Imagine predicting how a loaf of bread should rise while baking. You know the ingredients. You know the temperature of the oven. You understand the chemistry of yeast. From those factors, you can predict how large the loaf should become. Now suppose you bake the bread, and it rises only 80% of the expected height. Not half, not double, just slightly smaller than predicted. You might suspect an error in your measurement, but if you repeat the experiment dozens of times, and the bread keeps rising to exactly the same smaller size, you start questioning the recipe. That is the situation cosmologists find themselves in. The universe is forming structure slightly differently than predicted. Galaxies are clustering less strongly. Cosmic matter appears smoother, which could mean one of several things. Perhaps dark matter behaves differently than expected. Perhaps neutrinos, tiny ghost-like particles that flood the universe, influence cosmic structure more strongly than previously believed. Perhaps dark energy evolves over time. Or perhaps gravity itself behaves differently across enormous cosmic distances. Each possibility would require rewriting parts of modern cosmology, and each would affect the other tensions we have already discussed, because the parameters describing the universe are deeply interconnected. Change one, the others shift. Fix the Hubble tension, the S8 tension might worsen. Fix the lithium problem, the microwave background predictions might break. It is like adjusting one gear inside a clock, only to watch three others slip out of alignment. The machine works, but not perfectly, and here is the uncomfortable realization some scientists have begun to voice. These tensions might not be separate problems. They might all be symptoms of the same deeper issue. The possibility that our current model of the universe, the lambda CDM model, is incomplete. For nearly 30 years, the lambda CDM model has been the backbone of modern cosmology. It is elegant, simple, and astonishingly successful. With only a handful of parameters, it explains an enormous range of observations. The temperature patterns in the cosmic microwave background, the distribution of galaxies across billions of light years, the formation of cosmic structure, and the accelerating expansion of the universe. It tells us that the cosmos is made of roughly 5% ordinary matter, 25% dark matter, and 70% dark energy. It describes how tiny fluctuations in the early universe grew into galaxies and clusters. It predicts the large-scale geometry of space, and for decades, every major observation seemed to confirm it. But models in science do not survive because they are elegant. They survive because they match reality. And reality has begun to show small but persistent cracks. The Hubble tension, the S8 tension, the lithium problem, the strange alignment in the cosmic microwave background, known as the axis of evil, Each discrepancy on its own might be dismissed as a statistical anomaly or an experimental error, but together they form something more troubling, a pattern. And patterns make scientists uneasy, because patterns sometimes mean the underlying theory is incomplete. One of the physicists who has spoken openly about this possibility is Wendy Friedman, an astronomer who has spent decades measuring the expansion of the universe. Friedman helped lead major projects to refine the cosmic distance ladder, pushing measurements of the Hubble constant to unprecedented precision. At first, many researchers believed improved data would eventually reconcile the conflicting measurements. Friedman herself once thought so, but as new observations continued to arrive, the tension persisted, and the possibility that the model itself might need revision became harder to ignore. Another scientist deeply involved in this mystery is Adam Rees, the Nobel Prize-winning astronomer whose team helped discover the accelerating expansion of the universe. Rees has spent years refining the measurement of the Hubble constant using supernovae and Cepheid stars. Each improvement strengthened the result. The expansion rate remained stubbornly higher than predicted by the early universe model. Rees has described the situation as one of the most intriguing puzzles in cosmology, because both sides of the measurement appear extremely reliable. And when two extremely reliable results disagree, something important may be missing. And here is where the story becomes more philosophical. Scientific revolutions often begin this way, not with dramatic contradictions, but with subtle tensions, small inconsistencies in otherwise successful theories. In the early 20th century, classical physics seemed nearly complete. Newton's laws explained motion. Maxwell's equations explained electromagnetism. The framework appeared stable. Then tiny anomalies began to appear. The orbit of Mercury did not quite match Newtonian predictions. The behavior of atoms defied classical expectations. Light behaved both like a wave and a particle. At first, these were minor curiosities. Then they forced a complete transformation of physics. Relativity, quantum mechanics, entirely new frameworks for understanding reality. Some cosmologists now wonder whether the current tensions in our model of the universe might represent something similar. Not the collapse of modern cosmology, but the beginning of its next evolution, because if lambda CDM is incomplete, there are many directions science could explore. Perhaps dark energy evolves over time, changing the expansion history of the universe. Perhaps dark matter interacts with itself in ways we do not yet understand. Perhaps there exist additional neutrino species influencing cosmic structure. Or perhaps the laws of gravity itself change on the largest scales. Some theories suggest gravity behaves differently across billions of light years. Others propose entirely new particles or fields. There are even ideas involving additional dimensions of space. At the moment, these ideas remain speculative, but the tensions in the data have made them worth exploring, and that exploration is accelerating, because the next generation of telescopes is about to deliver a flood of new information. Across the world, a new generation of instruments is being prepared to study the universe with unprecedented precision. Some of them are already operating. Others are just beginning to collect their first data. And their goal is simple: find out whether the tensions we have been discussing are real, or whether they are illusions hiding inside our measurements. One of the most powerful of these new observatories sits high in the Chilean Andes. It is called the Vera C. Rubin Observatory. When fully operational, Rubin will repeatedly scan the entire southern sky using an enormous digital camera, one of the largest ever built. Every few nights, it will photograph billions of galaxies, not once, but again and again for 10 years. This project is known as the Legacy Survey of Space and Time, and it will produce one of the most detailed maps of the universe ever assembled. By observing how galaxies move and how their light is distorted by gravity, Rubin will measure the distribution of matter across cosmic scales with extraordinary accuracy. If the S8 tension is real, Rubin should detect it clearly. If it is a measurement artifact, Rubin's data may resolve the discrepancy. but Rubin is only one piece of the puzzle. Another key instrument is already operating in space. The Euclid telescope, launched by the European Space Agency, is designed specifically to study dark energy and the large-scale structure of the universe. Euclid maps the shapes of distant galaxies and measures how their light is bent by the gravitational influence of dark matter. This phenomenon is called weak gravitational lensing. By measuring tiny distortions in the shapes of millions of galaxies, Euclid can reconstruct the invisible scaffolding of dark matter that threads through the universe. This will allow scientists to measure the clumpiness of matter, the parameter S8, with far greater precision. If the universe is indeed less clumpy than predicted, Euclid should confirm it. If not, the tension may disappear. And then there is another instrument already changing our view of the cosmos: the James Webb Space Telescope. Webb is designed primarily to study the early universe, observing galaxies that formed only a few 100 million years after the Big Bang. But its extraordinary sensitivity also allows astronomers to measure cosmic distances with new methods. Some of Webb's observations are already contributing to the measurement of the Hubble constant. And so far, the tension remains. Short sentence: it hasn't gone away. Each new measurement seems to tighten the puzzle rather than dissolve it. Which brings us back to the question that now hangs quietly over cosmology. What if the model itself is incomplete? Because lambda CDM was never meant to be the final theory of the universe. It is a framework, a mathematical description built from the physics we currently understand. And like all scientific models, it will eventually be replaced or expanded as new evidence appears. The history of science suggests this is inevitable. The geocentric model of the universe once seemed perfectly adequate, until the motion of planets revealed deeper patterns. Newton's laws once seemed complete, until relativity and quantum mechanics revealed their limits. Each time, the old model was not discarded entirely. It became a special case inside a broader theory. Newtonian gravity still works extremely well for everyday situations, but Einstein's relativity describes gravity more accurately in extreme conditions. Some cosmologists suspect we may be approaching a similar transition, not the collapse of modern cosmology, but the discovery that our current model is only an approximation of a deeper framework, and that deeper framework might explain the tensions we see today. The Hubble tension, the S8 tension, the lithium problem, the strange alignment in the microwave background. Perhaps they are clues, pieces of a puzzle that has not yet fully revealed its shape, because the universe has a habit of surprising us. Every time we believe we have reached the end of discovery, a new observation opens another door, and sometimes that door leads to a completely new understanding of reality. One way to understand what might be happening is to imagine the universe as a gigantic machine. For decades, scientists believed they understood the basic components of that machine. Gravity pulls matter together. Dark matter provides the invisible scaffolding that allows galaxies and clusters to form. Dark energy pushes space apart, accelerating the expansion of the cosmos. Add these ingredients together, and the equations describe a universe that evolves from the hot plasma of the Big Bang into the vast cosmic web we observe today. For a long time, the machine appeared to run perfectly, but the tensions we have been discussing suggest that one of the gears may not be behaving exactly as expected. The expansion rate does not quite match predictions. Matter is not clustering exactly as strongly as the model suggests. The early universe produced the wrong amount of lithium, and the oldest light in the universe contains a strange alignment. Each problem is small, but they are persistent, and persistent problems often means something deeper is missing. Some physicists have begun exploring the possibility that dark energy might not be constant. In the standard cosmological model, dark energy behaves like a fixed property of empty space. No matter how large the universe becomes, the energy density remains the same. But if dark energy slowly changes over time, even by a small amount, it could alter the expansion history of the universe. That change might reconcile the early universe measurements with the local measurements of the Hubble constant. Several theoretical models explore this idea. Some propose that dark energy arises from a new kind of field that evolves slowly across cosmic time. Others suggest interactions between dark matter and dark energy. These possibilities are mathematically complex, but the underlying idea is simple. The universe might contain new forms of physics we have not yet discovered, but modifying dark energy alone may not solve every tension, which has led some researchers to examine the other major invisible component of the cosmos, dark matter. Dark matter was first proposed to explain the rotation of galaxies. Stars near the edges of galaxies move far faster than visible matter alone can account for. The simplest explanation is that galaxies are embedded in enormous halos of invisible mass. Over the decades, dark matter became central to cosmology. It helps explain how galaxies formed so quickly after the Big Bang. It shapes the cosmic web. It influences gravitational lensing. But despite decades of searching, scientists have never directly detected a dark matter particle. Large underground detectors, particle accelerators, cosmic ray experiments, all have looked for evidence. None have confirmed the identity of dark matter. That uncertainty has opened the door to alternative ideas. Perhaps dark matter particles interact with one another more strongly than we thought. Perhaps they decay over time. Perhaps they possess subtle properties that affect the formation of cosmic structure. Each possibility could influence the S8 tension, the discrepancy in how clumpy matter appears to be. Another possibility involves the behavior of gravity itself. Our current understanding of gravity comes from Einstein's general relativity, a theory that has passed every experimental test within the solar system and many beyond it. But those tests occur on relatively small scales compared to the size of the universe. Some theoretical physicists have proposed that gravity might behave slightly differently across billions of light years. In certain models, gravity weakens or strengthens over cosmic distances. In others, additional fields modify gravitational interactions. These ideas are controversial, but they are taken seriously because they could potentially explain both the Hubble tension and the S8 tension simultaneously. And this is where the story becomes both exciting and unsettling, because if any of these explanations turn out to be correct, they would represent new physics beyond the standard model of cosmology, a new chapter in our understanding of the universe. And history suggests that when multiple anomalies appear at the same time, science may be approaching one of those turning points. For scientists, moments like this are both thrilling and frustrating. Thrilling because they hint at discovery. Frustrating because the evidence is not yet clear enough to point in a single direction. Cosmology sits in an unusual position compared to many other sciences. We cannot run controlled experiments on the universe. We cannot create a second cosmos to compare with our own. We observe one universe, one cosmic history, and we must extract its secrets from the light that reaches our telescopes. That means uncertainty is unavoidable. Measurements improve slowly. New instruments must operate for years before enough data accumulates. And sometimes, apparent anomalies disappear when observations become more precise. But sometimes they don't. Sometimes they grow stronger. The Hubble tension is a good example of this. When the discrepancy first appeared, many researchers assumed it would vanish with better measurements. The early results relied on relatively small samples of supernovae and limited distance calibrations. Improved observations should have resolved the issue. Instead, the opposite happened. New techniques strengthened the disagreement. Astronomers began using alternative methods to measure the expansion rate. One approach involves gravitational lensing. When a massive galaxy lies between us and a distant quasar, the galaxy's gravity bends the quasar's light, producing multiple images. These images arrive at Earth at slightly different times because the light travels along paths of different lengths. By measuring those time delays and modeling the gravitational lens, astronomers can estimate cosmic distances, and from those distances, they can infer the expansion rate of the universe. These measurements are independent of the traditional cosmic distance ladder. and yet they also produce values closer to the higher expansion rate, closer to 73. Another technique uses the tip of the red giant branch. This method relies on a well-understood stage in the life cycle of certain stars. When low-mass stars exhaust the hydrogen in their cores, they expand into red giants. At a particular moment, their brightness reaches a predictable maximum before helium fusion begins. Astronomers can use this brightness as a standard candle, similar to supernovae, but based on different stellar physics. This method provides another way to measure distances across the universe, and once again, the expansion rate appears closer to the higher value. The tension persists. Short sentence, it stayed, which has forced scientists to confront an uncomfortable reality. If multiple independent techniques produce the same higher expansion rate, while the early universe predicts a lower one, then something about our cosmological model may be incomplete. But cosmologists are cautious. Extraordinary claims require extraordinary evidence. Before rewriting the physics of the universe, researchers must eliminate every possible observational error, calibration problems, instrument biases, unaccounted astrophysical effects. Years of work are devoted to testing these possibilities, and that process is ongoing. Meanwhile, the other tensions continue to evolve. The S8 tension has grown stronger as new gravitational lensing surveys improve. Projects such as the Dark Energy Survey have mapped hundreds of millions of galaxies. Their measurements consistently suggest that matter is slightly less clustered than predicted. Again, the difference is subtle, but persists. And then there are the puzzles in the cosmic microwave background itself. The axis of evil is only one of several anomalies researchers have noticed. Another is the cold spot, a region of the microwave background, slightly colder than surrounding areas. Some scientists believe it may be caused by a giant cosmic void along the line of sight. Others suspect statistical coincidence, but its presence contributes to the sense that the largest scales of the universe may not be perfectly uniform. Each anomaly alone is ambiguous. Together they raise questions, because if the universe behaves slightly differently than expected on the largest scales, the implications could be profound. To appreciate why these tensions matter so much, it helps to remember just how successful modern cosmology has been. Only a century ago, humanity did not even know that other galaxies existed. The Milky Way was believed to contain the entire universe. Today we can map galaxies billions of light years away. We can measure the faint afterglow of the Big Bang. We can simulate the evolution of cosmic structure on supercomputers using trillions of particles representing dark matter and gas. Those simulations produce universes that look astonishingly like the one we observe. Filaments of galaxies stretching across space, massive clusters sitting at the intersections of those filaments, enormous voids between them. The cosmic web, the agreement between simulations and observations, is one of the strongest confirmations of the lambda CDM model. But even within those simulations, researchers sometimes notice subtle differences. Galaxies in the simulations occasionally cluster slightly more strongly than the galaxies we observe. Cosmic voids may be somewhat larger than predicted. The differences are small, but they echo the same theme. The universe is almost behaving exactly as expected. Almost, and that word matters, because science advances in the space between expectation and observation. The history of physics is full of moments where small mismatches led to major discoveries. The motion of Mercury's orbit could not be fully explained by Newton's laws. That anomaly eventually helped lead to Einstein's theory of general relativity. The spectrum of atoms did not match classical physics predictions. That discrepancy gave birth to quantum mechanics. Each time, the problem began as a small inconsistency. Then it grew into a doorway to new physics. Cosmologists wonder whether the tensions we see today might represent a similar doorway. But opening that door requires evidence. Clear evidence, which means the next decade of observations will be critical. Astronomers are now combining data from multiple surveys, galaxy maps, gravitational lensing measurements, supernova observations, microwave background data. Each new dataset adds another layer to our understanding of the universe, and slowly, the picture is becoming sharper. Some researchers believe the tensions will eventually fade as measurements improve. Others suspect the opposite, that the discrepancies will grow stronger. And here is where the story becomes far more philosophical, because the universe may not be obligated to fit our expectations. The models we construct are attempts to describe reality, but reality itself may contain features we have not yet imagined. Perhaps dark energy evolves over time. Perhaps new particles influence the early universe. Perhaps gravity behaves differently across enormous cosmic distances. Or perhaps the universe contains entirely new phenomena we have not yet detected. For scientists, uncertainty like this is not failure, it is opportunity, because every unresolved question is an invitation to explore deeper. If the current tensions in cosmology truly signal new physics, the consequences could be enormous, because the standard model of cosmology is not just a loose framework. It is woven deeply into our understanding of the universe's history. From the first seconds after the Big Bang to the formation of galaxies billions of years later, every step of that history relies on certain assumptions. Assumptions about gravity, about the properties of dark matter, about the behavior of dark energy. Change any one of those ingredients, and the story of the universe changes with it. Take the Hubble tension, for example. If the expansion rate of the universe today is truly faster than predicted by the early universe model, something must have altered the expansion history between then and now. One possibility is that the early universe contained additional forms of energy or particles that briefly influenced its evolution. Some physicists have proposed the existence of early dark energy. In these models, a temporary burst of dark energy existed shortly after the Big Bang. It would have affected the growth of cosmic structures and altered the calibration of the cosmic microwave background. By the time the universe reached its current age, that energy would have faded away, leaving only the dark energy we observe today. Such a scenario might reconcile the conflicting measurements of the Hubble constant, but it introduces new questions. Where did that early dark energy come from? Why did it disappear? And why does the universe still contain dark energy today? Another idea involves additional neutrino species. Neutrinos are extremely light particles, produced in enormous quantities during the early universe. They barely interact with ordinary matter. Trillions of them pass through your body every second without leaving a trace. If an extra type of neutrino exists, sometimes called sterile neutrinos, it could slightly alter the early universe's energy balance. That change might influence the cosmic microwave background measurements, but once again, the evidence remains uncertain. Experiments searching for sterile neutrinos have produced mixed results. Some hints, no confirmation. Other researchers focus on the behavior of dark matter. In the standard model, dark matter is assumed to be cold and collisionless. That means dark matter particles move slowly and interact only through gravity. But if dark matter particles occasionally collide with one another or possess tiny self-interactions, they could change the way matter clusters across cosmic scales. Such interactions might explain why the universe appears slightly less clumpy than predicted the S8 tension. These models are actively being explored through simulations and astronomical observations. And yet another possibility lies in the nature of gravity itself. Einstein's theory of general relativity has passed every test within the solar system, but the distances involved in cosmology are vastly larger, billions of light years. Some theorists propose that gravity may behave differently across such enormous scales. Modified gravity models attempt to alter Einstein's equations in subtle ways. Perhaps gravity weakens slightly over cosmic distances. Perhaps additional fields influence gravitational interactions. These ideas remain controversial, but they are being studied carefully, because if gravity itself behaves differently on cosmic scales, it could reshape our understanding of the universe. And that is where the story gets far stranger, because the universe might not only be expanding faster than expected, It might also be revealing patterns that challenge one of the deepest assumptions in cosmology. One of the deepest assumptions in modern cosmology is deceptively simple. The universe has no preferred direction. On the largest scales, the cosmos should look roughly the same, no matter where you look. North, south, east, west. Every direction should contain roughly the same distribution of galaxies, radiation, and matter. When averaged across enormous distances, this idea is known as cosmic isotropy. It is part of the broader cosmological principle, the assumption that the universe is both homogeneous and isotropic on large scales. Without this assumption, many of our equations describing the universe would become dramatically more complicated. But more importantly, the evidence has long seemed to support it. Galaxy surveys show similar large-scale structures in every direction. The cosmic microwave background appears almost perfectly uniform. The expansion of the universe looks the same no matter where we observe it. For decades, these observations reinforce the belief that the universe truly has no special orientation. But the axis of evil challenges that picture, not dramatically, not conclusively, but persistently. When scientists examine the largest temperature fluctuations in the cosmic microwave background, they find that several of them appear to line up along a particular axis in the sky. That alignment should not exist if the fluctuations are purely random, and the alignment becomes more puzzling when researchers compare it with other cosmic measurements. Some analyses of galaxy distributions hint at similar large-scale directional patterns. Certain studies of quasar polarization, the orientation of light from extremely distant galaxies, have also suggested possible large-scale alignments. None of these observations alone proves the existence of a cosmic direction. Each could still be a statistical coincidence, but together they form an intriguing question. What if the universe really does have a preferred orientation? If that were true, it would challenge one of the foundational assumptions of cosmology. The universe would no longer be perfectly isotropic. It might possess subtle large-scale structure beyond the cosmic web. Some theorists have explored exotic explanations. Perhaps the early universe experienced anisotropic inflation, where space expanded slightly faster along one direction. Perhaps the geometry of the universe itself contains subtle asymmetries. Perhaps large-scale cosmic fields influence the formation of primordial fluctuations. These ideas remain speculative, but they illustrate how even a small anomaly can ripple outward into deeper theoretical questions. Because the cosmic microwave background is not just any observation, it is the earliest image we have of the universe. A snapshot taken when the cosmos was less than 500,000 years old. If that image contains unexpected patterns, those patterns could reflect processes that occurred during the very first moments after the Big Bang. Moments when the laws of physics themselves may have behaved differently, and that possibility leads to an unsettling realization. The universe we observe today may be only a partial expression of deeper physics that operated during its birth, physics we do not yet fully understand. When cosmologists talk about the birth of the universe, they are usually referring to an event called cosmic inflation. Inflation is the idea that, in the first tiny fraction of a second after the Big Bang, the universe expanded at an extraordinary rate, faster than the speed of light, not because matter was moving through space that quickly, but because space itself was stretching. In less than a trillionth of a second, the universe may have grown from subatomic size to something far larger than our entire observable cosmos today. This rapid expansion explains several otherwise puzzling features of the universe. It explains why distant regions of space have nearly identical temperatures. It explains why the geometry of the universe appears almost perfectly flat. And it explains the origin of the tiny fluctuations we see in the cosmic microwave background. According to inflation theory, quantum fluctuations, tiny variations in energy at microscopic scales, were stretched across cosmic distances as space expanded. Those fluctuations became the seeds of galaxies, clusters, superclusters, the entire cosmic web. Inflation is one of the most elegant ideas in modern cosmology, but like many powerful theories, it raises as many questions as it answers. What caused inflation? What field drove the expansion? Why did inflation stop when it did? Physicists have proposed many models. Some involve hypothetical fields called inflaton fields. Others suggest inflation may be connected to deeper physics such as quantum gravity, but no experiment has yet directly confirmed the mechanism behind inflation, which means the earliest moments of the universe remain partly mysterious. And if something unusual happened during those first moments, it could leave subtle imprints on the cosmos today, imprints like the ones hinted at in the cosmic microwave background, or anomalies that appear when we measure cosmic expansion, or discrepancies in the distribution of matter. These tensions might be signals, small echoes from the earliest moments of cosmic history, or they might simply reflect the limits of our current measurements. Cosmologists are careful not to jump to conclusions. Extraordinary claims require overwhelming evidence, but history has shown that the universe rarely behaves exactly the way we expect, and every generation of astronomers eventually discovers something that forces them to rethink the rules. Sometimes, the most important clues in science appear not as dramatic discoveries, but as quiet inconsistencies, numbers that refuse to line up, patterns that appear where randomness should dominate, measurements that improve year after year, but never quite agree. The tensions in modern cosmology share that quality. They are subtle, persistent, and increasingly difficult to ignore. One of the reasons these discrepancies attract so much attention is that cosmology has become an extraordinarily precise science. A century ago, astronomers could only guess the scale of the universe. Today we measure distances across billions of light years with astonishing accuracy. We map the cosmic microwave background to fluctuations of less than a millionth of a degree. We track the motions of galaxies through gravitational lensing and redshift surveys. And when precision increases, even tiny mismatches begin to matter. The Hubble tension, for example, is now measured with such precision that the disagreement between early universe predictions and local measurements exceeds 5 standard deviations. In statistical terms, that means the probability of the discrepancy being a simple measurement error is extremely small, small enough that many cosmologists now take the problem very seriously. The S8 tension has also persisted through multiple observational surveys. Independent teams using different instruments and analysis methods continue to find that matter appears slightly less clumped than predicted. The lithium problem has survived decades of stellar observations. Even the anomalies in the cosmic microwave background remain topics of ongoing debate. None of these issues individually overturn the standard model, but together they create a sense that something deeper may be waiting beneath the surface. A missing ingredient, a new piece of physics, or perhaps a subtle misunderstanding in the assumptions that underlie our models. One way to think about this situation is to imagine assembling a vast cosmic puzzle. Most of the pieces fit together beautifully. The image is clear, but a handful of pieces seem slightly out of place. At first you assume you have made a mistake. You check the pieces again. They still do not fit. Eventually you begin to suspect that the picture on the box might be incomplete. Cosmologists may now be approaching that moment, because the universe is not required to follow the simplest model we can imagine. Reality often turns out to be richer and more complicated. And when new physics appears, it rarely announces itself loudly. It begins with quiet tensions, small cracks in otherwise successful theories, cracks that gradually widen as observations improve. There is another way scientists sometimes approach problems like this. Instead of asking which measurement might be wrong, they ask a different question. What if none of them are wrong? What if every observation is correct, and the universe itself is simply more complicated than our model assumes? This idea has begun to attract attention in recent years, because the lambda CDM model, for all its success, is surprisingly simple. It describes the entire universe using just a small set of parameters: the density of ordinary matter, the density of dark matter, the density of dark energy, the expansion rate, the amplitude of primordial fluctuation. A few numbers, adjust them slightly, and the model predicts the evolution of cosmic structure across billions of years. That simplicity is one of its strengths, but it may also hide deeper complexity. The real universe might contain additional ingredients we have not yet identified. Imagine trying to understand Earth's climate using only temperature and atmospheric pressure. You could describe many patterns, but without including oceans, clouds, and atmospheric chemistry, the model would eventually fail. Cosmology may be facing a similar situation. Dark matter and dark energy account for 95% of the universe, yet we do not know what either of them actually is. We detect their effects, we measure their influence, but their true nature remains mysterious. If dark matter possesses unknown properties, if dark energy evolves over time, if gravity behaves differently at extreme scales, then the current cosmological model might only be an approximation, a remarkably successful one, but still incomplete. And that possibility excites many physicists, because new physics often hides precisely in places where theory and observation diverge. The search for those hidden pieces has already begun. Particle physicists are designing experiments to detect dark matter particles. Astronomers are mapping the distribution of galaxies with unprecedented precision. Theorists are exploring extensions to general relativity and alternative models of cosmic expansion. Each approach aims to test the same fundamental question: does the universe follow the rules we currently believe it does? Or are those rules only part of a larger story? If the tensions we see today truly point toward new physics, the implications would reach far beyond cosmology. Because the laws that govern the universe are deeply interconnected. Gravity shapes the motion of galaxies. Particle physics determines how matter behaves in extreme environments. Quantum mechanics governs the smallest scales of reality. And cosmology sits at the intersection of all these fields. When we study the universe as a whole, we are testing physics under conditions impossible to reproduce on Earth. The early universe reached temperatures and densities far beyond anything created in particle accelerators. The largest cosmic structures stretch across distances billions of light years wide. If new physics emerges from cosmological observations, it could reshape our understanding of fundamental forces. This possibility has motivated physicists to explore increasingly ambitious ideas. Some researchers are investigating theories involving additional dimensions of space. In these models, the universe we observe might be embedded within a higher dimensional structure. Gravity could leak into these extra dimensions, altering its behavior across large distances. Such effects might influence cosmic expansion or the growth of structure. Other scientists explore the possibility that dark matter consists of multiple particle species rather than a single unknown particle. Some of these particles might interact with one another through forces we have not yet detected. These interactions could subtly modify how galaxies form and how matter clusters across the universe. There are even hypotheses suggesting that dark energy itself might arise from quantum properties of empty space that we do not yet fully understand. In these scenarios, the vacuum of space is not truly empty. Instead, it contains fluctuating fields whose collective behavior drives the acceleration of cosmic expansion. These ideas remain speculative, but they illustrate the breadth of possibilities scientists are willing to consider as they search for answers. Because the tensions in cosmology are not just technical puzzles, they are windows into the unknown. Each discrepancy invites deeper investigation. Each anomaly challenges researchers to test their assumptions, and each new observation has the potential to transform our understanding of reality. The search for answers is already underway across the world's most powerful observatories. Every night, telescopes gather light that has traveled for billions of years before reaching Earth. That light carries information about the expansion of space, the distribution of matter, and the structure of the universe itself. Astronomers analyze these signals with extraordinary care, because sometimes the most important discoveries hide inside tiny details. a slight distortion in the shape of a distant galaxy, a faint shift in the spectrum of a supernova, a pattern in the oldest radiation in the cosmos. Each observation adds another piece to the puzzle, and as the data grows, so does the possibility that one of the tensions we see today may reveal something fundamental about the universe. In the coming years, several new projects will dramatically expand our view of the cosmos. The Vera C. Rubin Observatory will generate an unprecedented map of the sky, cataloging billions of galaxies and tracking their motion over time. The Euclid mission will measure gravitational lensing across vast cosmic distances, revealing how dark matter is distributed throughout the universe. The Nancy Grace Roman Space Telescope, scheduled for launch later in this decade, will study dark energy using wide-field observations of supernovae and galaxy clusters. Together, these instruments will produce an avalanche of data, and within that data may lie the answers to the questions troubling cosmologists today. Will the Hubble tension persist? Will the S8 discrepancy grow stronger? Will new patterns appear in the cosmic microwave background? Or will improved measurements eventually reconcile the current anomalies? No one knows, but history suggests that when observations reach new levels of precision, the universe often surprises us, because the cosmos is vast, and our understanding of it is still evolving. There is a moment that sometimes arrives quietly in scientific fields, a moment when researchers begin to realize that the questions they are asking may need to change. For much of the past half-century, cosmology has focused on refining a single framework, measure the expansion rate more precisely, map the cosmic microwave background more accurately, simulate the formation of galaxies with greater computational power. The goal was clarity, and in many ways, that clarity was achieved. We now understand the broad outline of cosmic history. The universe began in a hot, dense state. It expanded and cooled. Tiny fluctuations grew into galaxies and clusters. Dark matter shaped the cosmic web. Dark energy accelerated the expansion. That story remains remarkably successful, but the tensions we have been discussing hint that the deeper details of that story may still be incomplete. Perhaps dark energy is not constant. Perhaps dark matter has hidden properties. Perhaps gravity behaves differently across enormous distances. Or perhaps the early universe contained physics we have not yet discovered. The next decade of research may begin to answer these questions. New surveys will measure the expansion of the universe with unprecedented precision. Galaxy maps will reveal the structure of cosmic matter in extraordinary detail. Experiments searching for dark matter will continue probing the invisible mass that shapes galaxies. And theoretical physicists will explore new frameworks capable of explaining the tensions we see today. Science advances through this process. Observation, hypothesis, testing, revision. The models we build are not permanent truths. They are tools, and when those tools encounter new evidence, they evolve. When historians of science look back at moments of discovery, they often notice a pattern. Breakthroughs rarely appear suddenly. They begin with quiet anomalies, numbers that drift slightly away from expectation, measurements that disagree by just enough to raise suspicion. At first, scientists assume these discrepancies are mistakes. They refine their instruments, reanalyze their data, repeat the experiments. Sometimes the anomaly disappears, but sometimes it remains. And when it remains long enough, it forces a deeper question. Is the theory incomplete? The tensions in modern cosmology have reached that stage. Not yet a crisis, but no longer easy to dismiss. The Hubble tension continues to grow more precise as new measurements confirm the faster expansion rate in the local universe. The S8 tension persists as galaxy surveys reveal slightly smoother distributions of matter than predicted. The lithium problem still challenges our understanding of nuclear processes during the first minutes after the Big Bang, and the axis of evil continues to provoke debate about possible large-scale patterns in the cosmic microwave background. Each puzzle remains open. Each is being investigated by teams of researchers across the world, and together they remind us of something fundamental about science. Our understanding of the universe is always provisional. Even the most successful theories are subject to revision when new evidence appears. The cosmological model that describes our universe today may one day be expanded, refined, or replaced by a deeper framework. And if that happens, the tensions we see now may be remembered as the first hints that something larger was waiting to be discovered. There is a strange humility that comes with studying the universe. The deeper we look into the cosmos, the more we discover how small our understanding really is. Humanity has learned to measure galaxies billions of light years away. We have mapped the faint radiation left behind by the Big Bang. We have built mathematical models capable of describing the evolution of the universe across nearly 14 billion years. And yet, the majority of the cosmos remains mysterious. Dark matter, dark energy, unknown forces shaping the largest structures in existence. Even the expansion of the universe, something we can measure with extraordinary precision, may still hide physics we have not yet discovered. The tensions in modern cosmology remind scientists of this fact. They are signals that the universe may still contain surprises, not necessarily dramatic contradictions, but subtle clues pointing toward deeper layers of reality. In many ways, this uncertainty is the most exciting part of science, because every unresolved question is an invitation to observe more carefully, to measure more precisely, to imagine new possibilities. And the universe has always rewarded that curiosity. There is another reason scientists take these tensions seriously. The universe has surprised us before, more than once. At the beginning of the 20th century, most physicists believed the laws of nature were nearly complete. Newton's mechanics described motion. Maxwell's equations described electromagnetism. The remaining problems looked small. Then experiments studying atoms revealed behavior that classical physics could not explain. Electrons jumped between energy levels. Light behaved both like a wave and a particle. Matter itself appeared to follow strange probabilistic rules. Those anomalies eventually led to quantum mechanics. Around the same time, astronomers noticed a subtle discrepancy in the orbit of Mercury. Its motion did not perfectly match the predictions of Newtonian gravity. The error was tiny, but persisted. That discrepancy helped lead Albert Einstein to develop general relativity, transforming our understanding of gravity and space-time. In both cases, the breakthrough began with a small inconsistency, something that did not quite fit. The tensions in cosmology today have a similar flavor. No single observation has overturned the current model of the universe, but several independent measurements are hinting that the picture may not be complete. If future observations confirm these discrepancies, the implications could reach across physics. New forms of energy, new particles, new gravitational dynamics, possibly even deeper insights into the nature of space and time themselves. For now, scientists remain cautious. The evidence is intriguing, but not yet definitive. The universe may simply be reminding us that measurement is difficult at cosmic scales, or it may be whispering that something fundamental remains undiscovered. There is one final perspective that cosmologists sometimes consider when discussing these tensions, not as a solution, but as a reminder of how unusual our position in the universe might be. The cosmological models we use assume that the universe is statistically uniform on the largest scales, not perfectly identical everywhere, but roughly similar when averaged across enormous distances. This assumption works remarkably well, yet our observations are always made from a single location. One galaxy, one cosmic neighborhood, one vantage point inside the Milky Way. It is possible, though unlikely, that our region of the universe is slightly unusual. Perhaps the density of matter around us differs subtly from the cosmic average. Perhaps the large-scale gravitational environment in our part of the universe affects the way we measure expansion. These possibilities are carefully studied by cosmologists. So far, they do not appear sufficient to fully explain the tensions we see, but they serve as a reminder of an important truth. Our view of the universe is always limited. Every telescope looks outward from a single point in space and time, and the universe is vast beyond imagination. Step back for a moment and consider the scale of what cosmologists are trying to understand. The observable universe stretches roughly 93 billion light-years across. It contains hundreds of billions of galaxies. Each galaxy holds billions or even trillions of stars, and every one of those stars obeys the same fundamental laws of physics. From those laws, scientists have constructed a model capable of explaining how the universe evolved from the first moments after the Big Bang to the complex cosmic web we see today. That achievement alone is extraordinary, but the tensions we have been exploring reveal something deeper. The model works, but it might not be the final word. Somewhere inside the equations that describe the universe, small discrepancies are beginning to appear. The expansion rate measured in the nearby universe does not perfectly match the value predicted from the early universe. Matter seems slightly less clustered than expected. The first minutes after the Big Bang appear to have produced the wrong amount of lithium, and the oldest light in existence may contain subtle patterns we do not fully understand. None of these problems overturn modern cosmology, but together they suggest something important. The universe may still have secrets we have not uncovered, and that possibility has always been the engine of scientific discovery. What we know with confidence about the universe is remarkable. The cosmos began about 13.8 billion years ago in a hot, dense state. Space has been expanding ever since. Galaxies formed from tiny fluctuations in matter, created during the earliest moments of cosmic history. Dark matter provides the invisible scaffolding that holds those galaxies together, and dark energy drives the accelerating expansion of space itself. This framework explains an enormous range of observations. It predicts the structure of the cosmic microwave background. It describes how galaxies cluster. It models the growth of cosmic structure across billions of years. In many ways, the Lambda CDM model has become one of the most successful theories in the history of science. But what we do not know is just as fascinating. We do not know what dark matter is made of. We do not know what dark energy actually is. We do not know why the expansion rate measured today differs from the one predicted by the early universe. We do not know why lithium appears less abundant than theory predicts, and we do not yet understand whether the anomalies in the cosmic microwave background are statistical flukes or clues to deeper physics. Each unknown represents an open door, a question waiting to be answered, and the next generation of telescopes, experiments, and theoretical work may begin to reveal those answers. There is something quietly extraordinary about the moment we are living through in cosmology. For the first time in human history, we possess instruments capable of mapping the universe with breathtaking precision. Satellites measure the temperature of the cosmic microwave background across the entire sky. Space telescopes observe galaxies formed shortly after the Big Bang. Ground-based surveys chart the distribution of matter across hundreds of millions of light years. Supercomputers simulate the growth of cosmic structure using billions of particles representing dark matter and gas. The universe has never been observed with this level of detail before, and whenever measurement improves dramatically, two things usually happen. Some questions are finally resolved. Others appear for the first time. The tensions we have explored may be examples of that second outcome. They might represent the natural growing pains of an increasingly precise science. Or they might be the early hints of something deeper, a missing ingredient in our understanding of the cosmos, a new form of energy, a new particle, a modification to gravity itself, or perhaps an entirely new framework for describing the universe. History tells us that when science reaches the limits of its current models, discovery often follows. And this is where the story becomes both scientific and philosophical, because the tensions we see in the universe today force us to confront a simple truth. Our understanding of the cosmos is still evolving. Every generation of scientists inherits a model of the universe built by those who came before. They test it, refine it, and occasionally discover places where it no longer fits perfectly. That process is not failure, it is progress. The discovery that the universe is expanding once shattered the belief in a static cosmos. The detection of the cosmic microwave background confirmed the Big Bang. The discovery of dark energy revealed that cosmic expansion is accelerating. Each step forced scientists to rethink their assumptions. Each step expanded our understanding of reality. The tensions we see today may represent the next step in that journey, or they may eventually fade as observations become even more precise. Right now, we simply do not know, and that uncertainty is what makes this moment so compelling, because the universe still holds mysteries. For now, the universe continues exactly as it always has. Galaxies drift farther apart as space expands. Gravity pulls matter into clusters and filaments. The cosmic microwave background quietly fills the sky with the faint glow of the Big Bang. And somewhere inside the data collected by our telescopes, the answers to these tensions may already exist, waiting to be noticed, waiting to be understood. Science often advances in this way, not through sudden revelations, but through patient observation, careful analysis, years of debate and refinement. One generation of researchers builds on the work of another, and slowly, piece by piece, our understanding of the universe grows. But the tensions we have discussed remind us that even the most successful models remain provisional. They are maps, and maps are never the territory. The universe itself is always richer than the descriptions we create for it. And somewhere within that richness, new discoveries are waiting. The next answers will not arrive from a single telescope or a single discovery. They will emerge gradually from the combined effort of thousands of scientists working across the world. Astronomers will continue measuring the expansion of the universe with increasing precision. Particle physicists will search for the elusive particles that might make up dark matter. Theorists will test new models of gravity, dark energy, and the early universe. And new observatories will collect data far beyond what previous generations could imagine. Some of those measurements may confirm the current model, others may challenge it. Either outcome would represent progress, because the purpose of science is not to defend a particular theory. It is to understand reality as clearly as possible. And reality does not care whether our equations are convenient. It only reveals itself through observation. The tensions in cosmology remind us that the universe is still speaking, and we are still learning how to listen. For most of human history, the night sky looked calm, permanent, predictable, but over the last 100 years, we have learned that the universe is anything but static. It is expanding, accelerating, evolving, and the deeper we look into it, the more complicated it becomes. The tensions in modern cosmology are a reminder of that complexity. They tell us that even after decades of extraordinary progress, the universe still refuses to be completely understood. The Hubble tension suggests our picture of cosmic expansion might be missing something. The S8 tension hints that matter may organize itself differently than expected. The lithium problem challenges our understanding of the first few minutes after the Big Bang, and the strange alignment in the cosmic microwave background raises questions about the largest scales of the universe itself. None of these puzzles has been solved yet, but none of them has been ignored either. Every year, new measurements refine the data, new telescopes extend our reach deeper into space, and new theories attempt to explain what the universe might be telling us. It is possible that the tensions will eventually fade. Future observations may reveal subtle measurement errors or astrophysical processes we have not yet accounted for. But it is also possible that these discrepancies represent the first hints of new physics, new particles, new forces, new insights into the structure of space and time. If that happens, the current tensions may one day be remembered, the same way scientists remember the small anomalies that preceded quantum mechanics or relativity, not as problems, but as clues that the universe was preparing to reveal something deeper. Because the most important discoveries in science often begin with a simple observation. Something doesn't quite fit, a number that refuses to match expectation, a pattern that appears where randomness should dominate. Those moments force scientists to ask new questions, to test old assumptions, to imagine possibilities that once seemed impossible, and the universe has always rewarded that curiosity. Today, our telescopes are more powerful than ever, our simulations more detailed, our measurements more precise, yet the cosmos still manages to surprise us. And perhaps that should not be surprising at all. After all, we are trying to understand a universe that stretches across 93 billion light-years, filled with matter and energy we barely understand, governed by physical laws that we are still discovering. It would be stranger if everything already made perfect sense. Instead, the universe continues to present us with mysteries, quiet tensions in the data, small cracks in our models, signals that something larger may still be waiting to be discovered. For now, the equations still work well enough to describe the broad outline of cosmic history. But somewhere inside those equations, the details are whispering that the story might not yet be complete. And that possibility is what keeps cosmologists looking deeper into the sky, because the universe is still expanding, still evolving, still revealing itself one observation at a time. And the mystery we cannot fully explain has become the question we cannot stop asking.